So the next topic for electricity is power. We talked about power back in the previous unit. We defined power as the energy divided by time. And the energies we were talking about were kinetic energy or gravitational potential energy. We also talked about work. So now we're just going to use electrical energy and divide it by time. And that's going to give us the power of an electrical device. So in terms of the units, energy, as you know, is measured in joules, time is measured in seconds, so the units of power are joules per second. And we've given that a different name called a watt. So 1 watt is the same thing as 1 joule per second. So yeah, it's something divided by time. So in other words, it's how fast something is happening. So in terms of electric devices, power refers to how quickly they're sucking up power, or sorry, how fast they're sucking up energy, electrical energy. So if something's connected to a battery, it's how fast they're draining the battery, basically. And if it's connected to electrical outlets, it's how fast they're using up energy that you have to pay for from the electrical company. So in terms of the formulas, instead of using the previous formula on the previous slide, it turns out, and I'm not going to show you the derivation, I'm just going to list out the formulas here. It turns out that the power of an electric device can be calculated in terms of its voltage, current, and resistance. So there's 3 formulas depending on what variables you're given. If you're given voltage and current, the first formula here says you can calculate the power by multiplying voltage and current. If you're given voltage and resistance, then the second formula says you can calculate power by doing voltage squared divided by the resistance. And if you're given current and resistance, the third formula says you can get the power by doing the current squared times the resistance. You can calculate the power of an individual load, like an individual light bulb or something, or you can calculate the power of an entire circuit. So then you would use the voltage and current values for the battery, and you would use the equivalent resistance for the circuit to calculate the power for an entire circuit. One misconception I'd like to clear up is wattage. So oftentimes you buy things like light bulbs and they tell you how many watts the light bulb uses. However, this number, so in this case 40 watts, it is only the correct value if you hook it up to a certain voltage. So in this case, the packaging is pretty clear. If you hook up these light bulbs to 110 volts, then it's going to be 40 watts of power. 110 volts is the voltage that comes out of the sockets in Canada and the United States and other countries. However, if you travel other places, such as some countries in Europe and in Asia, the voltage out of their sockets is double, so it's 220 volts. So if you plug these light bulbs in over there, it's not going to be 40 watts. Okay, this 40 watt number only applies to 110 volts. The number that stays the same no matter what voltage you plug it into is the resistance. Okay, so this light bulb has a certain resistance, a certain number of ohms, and that number stays the same no matter what voltage you plug into. However, the watts do not. All right, so I'll do an example here. So for these slides, I'm going to have the power formulas written at the top, just for easy reference. So there's a mistake here, actually. 1 second. Should say 4.5. All right. Example 1. When 3 volts is supplied to a light bulb, the bulb draws 4.5 watts of power. what power will be drawn if the bulb, or by the bulb, if 6 volts is supplied to it? So I'm going to list out some information here. I'm making 2 lists here. It's the same light bulb, but in the first situation, they plug it into, and there's a mistake here as well. This 90, I changed it. Okay. In the first list here, it's referring to when the light bulb is plugged into 3 volts. So the voltage is 3 volts, and that's going to yield a power of 4.5 watts. And then they say, what if you plug the same light bulb into 6 volt source instead? So in the second list, the voltage is 6 volts, and I'm supposed to find out what the power is going to be. Okay, so 2 lists here. So how do I figure out this number? Well, I'm going to find the resistance value. So 2 slides ago, I told you the resistance stays the same no matter what voltage it's plugged into. So using my stuff in blue, I'm going to pick out a formula that's got voltage, power, and resistance. That would be the middle one right here. Pick out the formula to find the resistance. Okay, rearrange the formula to get resistance, plug in the numbers and calculate it, and it equals to 2 ohms. So that's the resistance value I can transfer over to my, my new list. Okay, so now I can find the power for the new voltage, which is 6 volts, which I'll plug into here. And now I can also plug in the 2 ohms that I calculated previously and calculate it out, and I get 18 watts. All right, so there's example 1. Example 2. In a series circuit with 2 light bulbs of different resistances, which bulb will consume more power, the bulb with a higher or lower resistance? So I drew that out. In the circuit construction kit. I've got 2 light bulbs in a series, so it's in the same pathway. I've set 2 different resistances, so one of them is 5 ohms, one of them is 10 ohms. So when I plug it to the battery, which one's going to use more power? Which one's going to be brighter? So take a couple of seconds to make a prediction, and then I'll connect it and see if you were right. Okay, so I plugged it in, and it's showing that the light bulb on the right is brighter. These yellow lines, the longer they are, the brighter it is. So it turns out that the one with the larger resistance is the brighter one for a series circuit. All right, and I wrote an explanation here on the slides. So in a series circuit, the current is the same through the whole circuit since there's no junctions. So we think of KCR, current splits up at junctions. There's no junctions in the series circuit. So the current's the same value everywhere. Both light bulbs have the same current value. So then if we look at the third formula for power here, P equals I squared R. Now if both light bulbs have the same current value, then whichever one has the higher resistance, the higher R, it's going to have the higher power. So that's why in a series circuit, the one with the higher resistance will have a higher power. However, in a parallel circuit, it's actually going to be the opposite. Okay, so it's the same question, but in a parallel circuit. So I created this parallel circuit, 5 ohm bulb in one path, 10 ohm bulb in the other path. If I were to connect it to the battery, which one would be brighter? Well, I already told you that the answer is going to be the opposite. Okay, so you can see here the lines on the lower resistance one are longer, so this light bulb is brighter. Okay, so that's the opposite answer. So why is that? So I wrote out the explanation here. In a parallel circuit, what's the same between these bulbs in parallel? So the currents are different now, okay? The currents are not the same in the two pathways anymore. But what is the same is the voltage of each light bulb. The battery is providing 9 volts, and kVr implies that every loop must consume 9 volts. So there's only one light bulb in each loop. So that means both light bulbs are each sucking up 9 volts. Okay, so the voltage is the same for both light bulbs. But now if I look at the middle formula, power equals voltage squared divided by resistance. So the two light bulbs have equal voltages of 9 volts. However, now the resistance is in the denominator. For this formula, the resistance is in the denominator. So a smaller resistance, meaning a smaller denominator, is going to yield a higher value overall for power. So that's why when the light bulbs are in parallel, the ones with lower resistance will have a higher power. And finally, I have this mixed circuit here. So I put in 4 light bulbs, A, B, C, and D. I labeled them. Now A, B, and D, I've made them all 2 ohms. And light bulb C, I made it 1 ohm. So when I hook it up to the battery, the question is asking you to arrange the bulbs from highest power to lowest power once they're connected. Okay, which one's going to be brightest, second brightest, third brightest, fourth brightest? So this requires a lot of work, actually a lot of explaining. So I'm just going to try to quickly go through it. First of all, light bulb A is going to be the brightest, and I wrote the reasons here. So light bulb A has the highest current, first of all, because all other bulbs are past the junction. So whatever current comes out of the battery, however many amps comes out from the battery or goes through the battery, is going to be the same amount of amps that goes through bulb A. And that amount of amps is going to reach this junction here and split up into 2 pathways. So whatever the current was at A, it gets split up at the junction. So that means the current through B and C is going to be smaller than it was through A. And the current through D is also going to be smaller than it was through A. So bulb A has the highest current. It is also tied for the highest resistance. 2 ohms is the highest resistance in this whole diagram. Therefore, if it has the highest current and the highest resistance, then according to the third formula, P equals current squared times resistance, it's got to have the highest power as well. So bulb A is going to have the highest power no matter what. Next, what about B, C, and D? Well, I'm going to compare B and C, first of all. B versus C. They're in the same pathway. Okay, what does it mean if they're in the same pathway? That means they have the same current. Okay, B and C have the same amount of amps going through them. But B has a higher resistance. So looking at the same formula, actually power equals current squared times R. They have the same current, so the one with the higher resistance, bulb B, is going to be brighter or have a higher power than bulb C. Okay, so A is the brightest, and I know that B is brighter than C. Now what about bulb D? Well, bulb D, I'm going to make a comparison to bulb B because they have equal resistances. So maybe I can make a comparison since they have equal resistances. And it turns out that bulb D has a higher voltage because of kVr. So looking at voltage, I got 4 volts coming out of the battery. So looking at the inside loop, 4 volts has to be balanced by A, B, and C. And then looking at the outside loop, 4 volts is balanced by A and D. So that means, like while bulb B has to share some of the voltage with bulb C, bulb D does not have to share any voltage with anything else in its path. Okay, so actually bulb D will have a higher voltage. So now looking at the middle formula with a higher voltage and the same resistance, bulb D has a higher power than bulb B.